Welcome to the sixth Build Test Solutions webinar and our final one for 2025. This month, we are focusing on ventilation and exposing the truth behind just how important this element of building performance and providing healthy homes is. The webinar will be presented by Dr. Richard Jack, our Technical Director, and moderated by Tanya Jane, our Marketing Manager.
Thank you, Tanya. So, I usually aim for about half an hour, but I enjoy putting this together and I came up with more content than usual. So maybe I'll stray over a little bit more, but hopefully I'll leave plenty of good time for questions at the end. I think that's the best bit, really. What I'm going to talk about today is how important ventilation is and why it's a little bit timely. If we learned some new things recently, what the failings of traditional ventilation assessments might be, and then just setting out two objectives, one which I think should be our minimum goal, and two which would be a slightly, I've called it a new way, maybe it's a bit highfalutin, but just going a bit above and beyond what would be minimum compliance. And then I wanted to set out a business case for effective ventilation at the end of the presentation. At the start, I'm going to talk loads about how important ventilation is, and sometimes it feels scary to put numbers to things, especially when we're talking about health. But I wanted to try and make the business case for it at the end, so I'll be interested to see how that goes down. So, kicking off with the importance of ventilation. So, to absolute basics to start with, and just to define some terms that I'll be using throughout. So what is ventilation? It's provision of fresh air and removal of stale air to control things like moisture, pollutants, and temperature. And some absolutely key definitions: two ways that air gets in and out of a building. So infiltration, which is uncontrolled air movement, so cracks and gaps, things that you're not calling vents. They're not a deliberate ventilation path. Deliberate's a bit of a funny word there, but I think it's quite relevant. And then ventilation, which is controlled air movement, which the most obvious thing would be fans and mechanical ventilation, but it also includes deliberate openings. So vents, trickle vents, windows, they're in your ventilation category, not your infiltration category. And then very broadly, how is this ventilation supposed to work? And I think it's interesting and useful to think about this in real broad terms about what's supposed to happen. So we've got three prevalent types of ventilation. So natural ventilation means no fans, and air is moving into and out of the building through all openings. So through our deliberate openings, but also through our accidental openings. And we're relying on the wind going past the building and the temperature difference between inside and outside to drive some air movement from inside to outside. And that's really variable. So on a windy day, we could get a lot of air movement, but on a still day, and if the temperature is very similar inside to outside, there's actually not very many driving forces to make air movement happen. And I think it's also interesting to think that we're talking about all openings there. So that fresh air from outside is coming through sometimes some pretty unusual leakage paths, uncontrolled leakage paths, and it might also be going through places that make the air a little bit less fresh by the time it arrives in the building. So it could be coming through a subfloor void, which is damp and might have various pollutants in there. Extract ventilation, so it is what it sounds like. We're removing stale air, so we're pulling air out with a mechanical fan, and then that fresh air is coming in through all these openings again. So the trickle vents, their purpose is to provide a route for the fresh air to come in to replace the stale air that's pulled out of usually the wet rooms. But again, that air is coming in through all of our openings, so any air gap, you're going to introduce air through there. So it's not necessarily just the vents, it's also through all our cracks and gaps. So again, we're thinking about, is that air fresh by the time it comes in? And then top level ventilation would be supply and extract. So we're going to supply fresh air with a fan and a duct, and we're going to remove stale air. We're doing both. So we're both supplying and removing. And that works best when we've got fewer other openings because we want to totally control. We want to say we're putting this air in and removing that air. We don't want an uncontrolled air movement which will interrupt that airflow. It also means when you think about your extracts, what we want to do there is pull in fresh air, and if we're controlling for moisture, relatively dry air, and if we're removing from a wet room, if that wet room is very leaky or it has a trickle vent, then you could be pulling the air in through the trickle vent and bypassing the ventilation of the rest of the building. So it's a whole system, you know, the fan and the openings all working together, including your deliberate and your accidental openings. And then ventilation is a balance. So in this country, most buildings are not super airtight, and we're relying to some extent on infiltration, so accidental air movement through cracks and gaps, to provide our fresh air. And the more airtight the building is, in our regulations, we say, okay, then you have to provide more mechanical ventilation, more deliberate openings, because we haven't got those cracks and gaps. So as the building gets more airtight, the balance shifts gradually from infiltration to ventilation, because the infiltration goes down because the building's becoming more airtight. Now, that is what is. It doesn't necessarily mean it's best practice. Infiltration is a much less controlled and basically good way to provide fresh air into the building. So ideally, we would be talking about using primarily ventilation so we can control where the air is coming from. But just some key concepts to start off with: infiltration, ventilation, how it differs between different buildings, and particularly more airtight buildings tend to have more ventilation. In this country, less airtight buildings we allow in the regulations to have their fresh air provided more by infiltration. So now this bit's going to get quite techy, which I don't apologize for because I think it's really interesting stuff. I quite enjoyed pulling it together and just reflecting on how big of a deal providing enough ventilation for a building is. And really, it is a very serious hazard. And we see that the building regulations and AWAB's law come and gradually tighten up the requirements for ventilation. And this stuff is why that's happening, because we're recognizing that it's a really serious issue. So poor ventilation increases your damp and mold risk, but it also increases the chances of the risk of viral transmission, and it increases the amount of pollutants in the building. And in turn, these impact these health issues that people suffer. And more than half of the top 10 leading causes of death in the UK are directly related to poor ventilation. So we're talking about a really serious risk for people's health, of the same order of illnesses that people would be thinking of, you know, heart disease, cancers. We're talking of something of the same order of importance of that, just in terms of purely dying. But it also has an impact on your mental health, a proven impact on your mental health, and that isn't hard to empathize with. If you're living in a damp house, it's very sad, and it has a serious impact on your mental health, and it has an impact on your concentration. If you're thinking about CO2, high levels of CO2 can be dangerous, both for your health, but also for your productivity. So poor ventilation impacts 64% of those top 10 leading health risks in the UK. The NHS estimates an annual direct cost of £900 million caused by illnesses that are caused by poor ventilation. And the really sad thing about this is that it affects vulnerable people the most. So children and older people are the most likely to suffer from these illnesses associated with poor ventilation. So it is a big, big deal. It's really important. It's also a serious hazard for buildings. So moisture damage, both on internal surfaces, but also interstitial. And remember when I was talking about where fresh air is coming from, if we're drawing air through leakage paths which go between building elements, that air is bringing some moisture with it. And we could by poor ventilation control be causing damage to the building, both inside that we can see and in between parts of the building, which are much more hard to see. Mold, you could be bringing insects and dust and bits in with your ventilation if you've got poor control, which can cause building damage. So it's a serious hazard and a serious cost for buildings, and it's expensive and difficult to deal with, especially if you're a landlord. It can cause a lot of problems, which cause you a lot of issues on the bottom line, as well as affecting the health and happiness of your residents. And I put in that title at the start in the contents, what I put a word now, what's changed recently. So under PAS 2035, it's the first time we've ever done large scale airtight measurements in existing buildings. So we were doing that, and we are doing that, to think about ventilation sufficiency. But what we've also found, sort of as a byproduct, almost by accident, is a lot more about how airtight buildings are. And Dr. Ben Roberts at Loughborough University did a really good bit of work for DESNES recently, which has loads and loads of information about that. So if you're really interested by this little flavour, that's a good reference to go and seek out. But just looking at this distribution of air tightness, this is around 34,000 buildings. And here I've separated the buildings out by age band. And as the buildings get newer, they're getting more airtight. But what I think is quite interesting about that is that for almost all of the age bands, until you get to K, L, and M, so we're talking, I think that's post 2011. I need to revise my age bands to be absolutely confident on the exact year, but really quite new buildings. Buildings of all these different ages have really similar air tightness. So we might sort of guess that an older building, you know, an age range A, pre-1900 building, is going to be super leaky and much less airtight than newer buildings. But actually, the results show that that's just not the case. And also on here, on this chart, I've got these are cumulative distributions. So you're all the buildings rising up to 100%. You can see that almost all the buildings are more airtight than RD SAP assumes. So around 85% of all buildings are more airtight than it's possible to get in RD SAP. And that has an impact for EPCs, which I'll talk about a bit later. But also it just means that really, I think buildings, existing buildings, especially older buildings, are more airtight than we expected. And especially there are more airtight buildings that are old than we expected. So as well as the average, there are some really airtight buildings that you just would never have guessed are going to be airtight buildings. And that has a big impact when you're thinking about ventilation. When we say that if a building's more airtight, we need to provide more ventilation, that's what the regulation is based on. So if you don't know the airtightness, we're really guessing about whether it requires that ventilation or not. I should have moved on here and it would have given me the age bands. I wouldn't have had to remember them. And I got the wrong year. I should have said 2007. But what I just had this slide in here to say specifically, isn't it interesting that only these two age bands, L and M, so post 2012, that's really when we've seen the buildings get much more airtight, despite airtightness testing being in building regulations since 2002. So I think that's a bit interesting, and really the narrow grouping of all those other age bands I think is quite remarkable. And this is just highlighting that what I said earlier, where here we're looking at buildings which have an air permeability at 50 pascals of lower than either 3 meters cubed per meter squared per hour or 5 meters cubed per meter squared per hour. And I've chosen those two parameters because the building regulations sets them out as airtight buildings, very airtight buildings. And you can see that even in these old buildings, pre-1900, we've got more than 10% of them are classified under the building regulations as very airtight. So you can't just assume that an older building is going to be leaky. The results show that that assumption is really can't be trusted. And then I wanted to, this paper really interesting, and here Ian Hamilton and his team, he's based at UCL, were looking at the health impacts of energy efficiency interventions in the UK. So what would happen if we did if we did retrofit works to all buildings in the UK. So thinking about existing buildings, and particularly what would happen in various situations of ventilation provision. So the blue bar there, or purpley blue bar, is what if we provided ventilation as per regulations, okay? Which it really should be the minimum that we achieve. And here we're using a metric called QALYs, quality adjusted life years. It's a metric used in medical circles to quantify how big of a benefit you can get from some intervention. And the number that's come up here is 2,500 QALYs per 10,000 persons over 50 years, which, just like you, I've no idea what that meant, although it looked good. And when I did some research to sort of compare that to stuff, it was saying that's about a tenth of the importance of people smoking. Okay, it's about the same as breast cancer screening. So that's what I was saying earlier, that the benefits of ventilation, of good ventilation, are really tangible, important, of the same order of some really serious health impacts and things you could do to improve people's health. So if we can provide ventilation as per regulations, there will be a lot in it for us as a country and as individuals. Equally, if we don't provide added ventilation, we're going to cause a lot of health risk. So can we do it? So the key takeaways from this introduction that I wanted to try and communicate was that ventilation means fresh air. Ventilation in this country in particular, but actually most places, includes deliberate ventilation, mechanical or just openings, but we're also relying on accidental air movement through infiltration. Therefore, the air tightness of the building and its ventilation are related in real life. Perhaps not in perfect ventilation design, but under regulations, and as buildings are, that is true. Poor ventilation is an absolutely key health risk of the order of really serious health issues. You can put this alongside thinking about treating cancer. It's a medical issue, and it costs health and money to get it wrong. So what is the issue with traditional ventilation assessment? So I think first absolutely key thing is that air tightness is really variable and really unpredictable. Now, I've shown this slide, I showed it at our last webinar when I was talking about heat loss. It's just as relevant now that I'm talking about fresh air provision and ventilation. So if we say under the current regulations and under current situation, the amount of infiltration is important for how much ventilation there is in a building. If we don't know the amount of infiltration, then we're really in trouble. And actually, buildings that look the same and have really similar building characteristics, so that if we did a top-notch job of visual surveying, we really couldn't guess how airtight a building is. I do it a lot. Whenever I'm doing a measurement, I'll have a guess, and I'm always surprised. And I've measured heat loss and air tightness in thousands of buildings, and I'm still freshly surprised every time. So it's something that you just can't guess accurately. If you use this stat, the 95% prediction interval, which is a statistical way of saying, based on the measurements we've done already, this is a sample of several thousand solid wall semi-detached houses, how confident can I be in estimating the air tightness of the next solid wall semi-detached building that I come across? And my confidence range in my estimate should be around plus or minus 75% of the mean. So, you know, I'm guessing. And if it's important, ought we be guessing? The other part of the fresh air provision situation is ventilation, mechanical ventilation. Now, it's interesting that it's required that you commission ventilation when you put it in, and you ought to measure the flow rate through the fan, but it doesn't have the same apparatus around it as air tightness measurement does, so that we don't have an ongoing register of measured in situ fan flow rates. And I think that's a real failure, actually, because we don't know what's happening in practice. But in I mean, it's not a big study, but in the largest study that I could find, it was found that 9 of 55 intermittent extract fans actually delivered as per building regulations approved document F. So that means the vast majority weren't. Only one of 25 continuous fans met the flow rates set out in approved document F. So it's absolutely endemic that the fans aren't delivering as much flow rate as they ought to under the regulations. And I found that when I'm doing my own measurements, it's a really common situation. So I think a really big step we could make there is, first of all, start actually measuring and paying attention to the results we get back. But also we should start to saw the measurements so that we can get a picture of what's happening. Another new thing that's happened is that under the background ventilation testing standard set out by the Insulation Assurance Authority, we started to look at room level air tightness. So we have a sample now of, as of yesterday, 49,816 room level air tightness measurements. And here I'm looking at air changes at 4 pascals. And what's interesting here is that the variability of the room level air tightness is even higher than the variability of building air tightness. And what you can have is a really airtight room or several really airtight rooms within a leaky building. If I think about the last 2 houses I've lived in, the previous house I lived in was a purpose-built flat, and it had an internal bathroom, and it was super, super airtight, even with quite a significant door undercut. And that room, until I provided more ventilation to it and allowed it to be more connected to the rest of the building, had massive mold issues, even though the building, in that case, the building was quite airtight. I think about my current building. When I moved in, the building was pretty leaky, more than 10 AP50. But we had one bedroom that was super airtight, and that was even despite it having formerly had a warm air heating system. So it has a door overcut in this case. But the room itself was really airtight, and it had trickle vents. It needed more ventilation. So if we want to provide ventilation suitably across the whole building, I think we need to start thinking about at room level, not just about a building level. Or continue to, I suppose, rather than start. You can see there's 49,000 measurements there. So the key part of why I think traditional assessment without measurement doesn't work is that it's just so proven that visual inspection isn't sufficient to see what's really happening. That means that if we have a design, install it, and then assume that it will work as per design without measuring it, we're, as the boss says, we're dancing in the dark. We're trying to control something we just don't know. So can we move away from just using these assumptions and assuming that things will do what they say on the sticker, or that buildings will be as airtight as we guess they are, and provide measured evidence to prove that we have done what we thought we had? I was considering singing there, but I think for the good of everyone, I won't give a rendition. So here's what I think we ought to be doing. And I remember I said I'd have our 2 levels. So this is what I think is absolute minimum risk-aware compliance. So we're complying with both the spirit and the wording of regulations. What regulations am I talking about? I'm talking about primarily building regulations approved document F about ventilation flow rate, which I think is a really great document, and it's pretty good for us that we've got a well set out document that we can work against. Okay, so we're not having to invent a new set of guidelines, which would be really difficult. We've got a good set of guidelines we can work against. PAS 2035 and background ventilation testing, really that is about ensuring that we're delivering the building regulations, but it also has this concept of room level air tightness. And Wattob's law, I think, is also very relevant here, because although it's not setting out levels of air tightness and fan flow rates that should be provided, it is saying that we need to protect against the hazards of mold risk as of 2026, cold and overheated buildings. And in order to effectively protect against those hazards, I think we need to be thinking about ventilation properly. And then one thing, I wouldn't say it's as central to ventilation, but it's worth pointing out that when you're measuring air tightness, and we've seen that 85% of buildings are more airtight than is expected in the RD-SAP calculation, which provides the EPC, it's also relevant to thinking about your EPC rating and meeting minimum energy efficiency standards, because we can be using that evidence to accurately reflect how airtight the actual building is and affect our EPC ratings. And what are the tools we need to deliver this new way of thinking about ventilation, or not really a new way of thinking about ventilation? What are the tools we need? So we need to think about how much air comes through the fan. So we need some sort of flow rate measurement, either a powered flow hood, if you're thinking about really low, relatively low flow rates, or an unpowered flow hood with an effective straightener if we're thinking about higher flow rates. And if we're thinking about the air tightness of the building, we need to measure the air tightness, and you could do that either with a pulse kit or with a blower door. So there we have measured air tightness and ventilation flow rate. Those are the things that we feel like we're in control of as surveyors of, or providers of, or builders of the building. Can we actually make sure that they're performing as per spec? That's why I say it's a minimum requirement, in my opinion. So we're going to measure the air tightness, and we're going to determine the level of mechanical ventilation and general ventilation that's required according to approved document F. And then we're going to measure the flow rates and check that it complies with the minimum specification, the minimum regulated limits and the specification for the ventilation plan. So basically, we're going to go and see if the ventilation plan is working as designed. Kind of crazy that we're even thinking about whether that would be business as usual, in my opinion. Can we go one step beyond? So can we look at performance in use and see whether we've got enough ventilation? So what are we missing from our previous, our minimum level? So we're missing something about ongoing performance. So what happens over time? Does the fan degrade? If we've got filters in the ventilation system, do they start to get blocked? Does anything happen with the fabric? Does it get more or less airtight? We're missing a lot to do with context. So what's the occupancy level in the building? What are the people doing in there? How much they know about ventilation provision? How well heated is it? What's the weather like? And especially building sheltering. If we're relying on air movement from the wind traveling across the building to create a pressure difference to generate infiltration, that is really heavily affected by the situation of the building. And we've also missing, I think, a little bit of risk protection from some fundamental knowledge gaps. I think there still are, which is, how does air tightness relate to infiltration in use? When the weather changes, when we've got different sheltering levels, how do we account for that? What actually is happening for air movement in use? I think we still don't know some of those questions. So can we have something that protects us from that to see whether the ventilation is actually working? Yeah, one more tool in the box. This is actually pretty simple ongoing monitoring, which is becoming more and more common. So minimum, I'd say, would be internal temperature and relative humidity. You could have others in there, so CO2 perhaps, to think about pollutants or particulates. So it's not limited to that, but I say those as a minimum. And I think what's really, really important is that we don't just monitor like a constant stream of temperature and relative humidity data. It's quite hard to interpret. So let's benchmark it against the guidelines that are set out in Part F of the building regulations. Again, it's saying here are some sensible protections. So we've got something that we can benchmark against. You might also use a mold risk indicator, so to give you a risk indication of how much mold risk there is in the building. And we can monitor over time for changes, and we can pick out buildings which are particularly in need of interventions, and also buildings we can pick out ones which are most appropriate for detailed measurements, which have a higher cost. So here I'm trying to paint a sort of virtuous circle where we have ongoing monitoring to ensure that we're delivering what we said we would in practice. Where we have confusing situations, we go and measure the airflow, so the air tightness, the ventilation flow rate, perhaps the room level air tightness as well, to see is it as per spec. And really importantly, we have well-documented evidence. So those measurements, we keep a record of them. We use them to evidence that we're complying with the building regulations and that we're having proactive resident protection. So finally, I wanted to try and make the business case for effective ventilation. And I'm an engineer by everything, so not my natural area, but see what you think about this. So what does it cost us to get ventilation wrong? Here's a fan that's all clogged up and I'm sure can't be delivering what it says on the tin. So I think the budget lines, what we're talking about here, are reactive maintenance, complaints handling. I mean, you can read them. There's no point in me reading them as well. So really clear budget lines, which housing providers in particular are worried about, and does cost the bottom line. And then, of course, lives. We started off with how important this is for health. So we're also talking about people's health and providing a good living space for people, or ourselves if you're thinking about your own building. So what we want to avoid is trying to get into this poor ventilation trap where we have an ineffective assessment. We don't know what the air tightness is. We don't actually know what the fan flow rate is. We get high relative humidity. We get moisture issues, mold issues. We get complaints. We go and do something about it, which doesn't address the core issue. And we go right back to the start. And we're traveling around and around this loop, not improving the situation for people and costing ourselves a lot of money. So let's consider a common business as usual scenario. We've got a damp and mold prone dwelling, and we don't know its air tightness and fan rates. And as a result, we've got regular reactive visits and periodic redecoration. Now let's think about the business case. Say, I'm just using round numbers here. We've got a portfolio of 1,000 dwellings, and 5% of those are in that case in the previous slide. So they're suffering from ventilation issues. Our business as usual says that we'll go and do something like a mold wash, and we'll have to respond to a complaint and an inspection. And I reckon that costs of the order of £1,000 per property for each of those cases where we have an issue. So over the whole stock, 5%, that's 50 buildings a year. We're talking about 50 grand cost per year, and we're repeating that every year. Now, if we went and did air tightness and flow rate measurements, we might expect a cost of around £150 per building. So if we did all of the buildings, that would be a cost of £150,000. Perhaps we could be cleverer than that and target the 30 which have most common issues, or we could even use our monitoring to target our measurements, and that would reduce, if we only did 30%, that would, or a third, that would reduce our costs down to £50,000. And what we're trying to do is understand the root cause and address it once, rather than having this repeated issue. So scenario A, we do what I would love us to do, and we measure every building in that stock of 1,000. And by doing it, we reduce the repeat works by 50%. So I said there's some uncertainty, so we don't completely remove ventilation issues, but we halve the scale of the issue. So we have an annual saving of £25,000. We would have a payback on that one-off payment to measure all the buildings of 6 years. Over 10 years, we'd be looking at a return on investment of £100,000 for that 1,000 stock. If you had a bigger stock than that, you're obviously talking about bigger numbers, smaller, the opposite. What about if we were smarter and used this targeted works? Then given the lower cost, we'd have a payback of 3 years. Here I'm saying that because we're targeting and not measuring all buildings, we'd only have 30% lower repeat works because we haven't measured every single building. So our annual savings are a bit lower, but our payback is still within 3 years, and we actually end up with the same 10-year payback from measuring that smaller sample of buildings. So there's a really clear, pretty short payback, and return quite large return on investment for doing the measurement. We also have these series of indirect benefits. So we've got better compliance, we've got right first time, high quality service, and therefore a good reputation, healthier, happier residents. Again, I'm just reading the slide, but you can see that there's lots of different, less easy to quantify benefits just coming from doing this measurement. So it makes a virtuous circle and it pays for itself. It feels like a cost, but the value is such that even with these quite conservative estimates, you're earning money by doing the measurement. So finally, as we're coming up to the end of the year, can we have a New Year's resolution where we actually go and do more of this stuff? So can we start targeting measurements? Can we test problem properties, check if we're really complying with both the word and the spirit of building regulations, and have proactive compliance? And can we do something basic, which I fear doesn't happen in every case, where we actually, when we take a measurement, we keep a good record of it, we keep it stored against the building, and we compare that measurement with some sensible benchmarks like I provide in the building regulations. We don't just have a number that we're struggling to interpret whether it means it's good or bad. And if you're a surveyor or going and visiting buildings, can we add value to each visit? So if we add these measurement tools to the toolbox, we can deliver effective ventilation. And as we're already there, the marginal cost of doing these extra measurements becomes lower, and we can deliver the business case that I described earlier to our customers. That's our campaigning New Year's message heading into 2026. So an extra 7 minutes compared to usual, but hopefully interesting content, and I look forward to a bit of conversation now.
Fantastic. Thank you, Richard. As ever, incredibly insightful, and hopefully you will find that incredibly useful as well. We will ask if questions can just be popped into the Q&A or into the chat, just so that we can keep a track of the order that they've come in, and that will make life a lot easier for going through everybody. We have had a couple of questions in just asking for the sources of some of the data, Richard, which I'm sure we can sort out afterwards and make sure they're included when we share the content at the end, mainly on the NHS costs and on the distribution of building air tightness. So we'll make sure all that's included in your follow-up email.
When we share the slides should have all the sources in as links to the website, so you get the sources when the slides are shared.
Yeah, absolutely. And at the moment, you're all being incredibly coy. There must be some more questions. Is this going to be a first for one of our webinars where we've ticked all the boxes for you?
I can see a question from Marcus there. Remind of the source of the distribution of building air tightness. That's from our own database of air tightness measurements. So all pulse measurements there. That's where the data comes from.
Absolutely. Okay, we have had a question from Emily. Interested on a stock level, how would you recommend selecting high-risk properties to survey based, I assume, on stock data?
Yeah. So my number one, I used to work for a main contractor doing repairs and maintenance contracts, and we would have picked the buildings which have most complaints as a first signifier. And you might also find that you have buildings of a similar type, or even apartments within the same building where you have more shy residents that don't complain as often but might have similar issues. So that might be a good place to start. And then also, if you're monitoring temperature and relative humidity, you could be using those flags as somewhere as a flag to go and do more detailed testing.
Fantastic. I think the next question is more of an observation for discussion from Jim. If commissioners are self-certificating that a system is working to building regs, surely that's a weak link.
Yeah, I think it is, and I think the measurements prove it, to be honest. I don't know why it doesn't have the same sort of apparatus and structure as air tightness testing. I think there's a lot of benefit to that, and I think it would help address what I agree is a weak link.
Yeah, Absolutely. And then from Peter, what about the £150 testing cost? That seems a bit low.
Yeah, I wondered about that as well. I think that testing cost is really related to volume. So in that case, where I was thinking about a stock of 1,000 buildings and you're rolling out air tightness and ventilation testing across a stock of buildings, so you've got regular ongoing work and they're almost certain to be fairly close to each other, so your traveling times would be lower. I felt it was justified to include that price, perhaps a little bit keen. But yeah, I don't as BTS, we don't set a market rate for testing. So yeah, you could feel free to rerun the numbers with a higher cost, and actually you still get pretty good business case come out of it.
Absolutely. And the next question is, should Part F stipulate a specific fan size based on room volume with a safety margin of 200% built in by manufacturers to allow for dirt degradation, reducing flow over time?
Good question. It's difficult to know how to cope with degradation of a fan over time. If you don't clean it, it is really significant. But the action to solve it is also really easy. Like a pretty basic clean will get that fan running again. So to be honest, I don't know the answer. I can definitely see the logic of where you're coming from. And it's a really common issue that I've seen in houses of all types when I go in, that the fans are furry basically, and it's not a nice job, and it's often you need something to step up on to get to it, so it's an easy one to put off. Yeah, it's interesting where you get that blurred line between what you can provide at the stage of building or retrofit and what the ongoing maintenance ought to be for the services. Another thing that I've seen really commonly is with mechanical ventilation heat recovery systems, the filters don't have a regular cleaning schedule as part of the housing providers' normal services, and the residents most of the time aren't even aware that they're in there and need either replacement or cleaning. So that maintenance is just as important as getting it right at the start.
Yeah, absolutely. And that's kind of it's an education piece, isn't it? Question from Will. Is there a simple guide to the different ways of measuring flow rates, such as air changes, litres per second, Q50, N50? It gets a bit confusing.
Yeah, well, if you're thinking about air tightness, actually the standard for air tightness measurement, CIBSE TM23, is a really useful document and quite approachable. So I would recommend going there. You'll also find on our website there's a tool to convert between different metrics. So you can convert between your AP50s and your N50s and your Q50s and your Q4s, and it is terribly acronym heavy. So those two I think would be useful references. For fan flow rates, actually there's a good BISRIA guide on measuring fan flow rates, and that's probably the best place to go. I can't remember the document number off the top of my head, but it's a little bit less well covered in both guidance and regulation than air tightness measurement, I'd say.
Thank you. And Tarek has asked, this may be a silly question, it's never a silly question. How do you meet the sweet spot between ventilation and heating, especially in winter?
Yeah, this is a real, it's not a silly question, but it's a difficult question. So you need enough fresh air, and we've proved that it's important. But of course, if you're bringing air from outside and you haven't got heat recovery, it's cold, and so it increases your heating bill. So there's no easy answer really. If you can't afford the heating and you're trying to choose between the two, it's difficult, because cold temperatures actually have a similar health risk to poor ventilation on those quality metrics I showed earlier. What I'm a massive fan of is warm rents. That's just my personal opinion. that a building is supplied with an adequate level of heat, and that allows people to ventilate properly without having to choose between the two. But it's almost getting into it's getting into something beyond the engineering of measuring the flow rate. I can see a couple of people have filled in my blank on the BISRIA document number, so thank you very much.
Next question comes from Jeffrey. How relevant are ventilation and air tightness measurements to commercial buildings?
Yeah, totally relevant, just as relevant as domestic buildings. They're buildings that we spend a lot of time in. Just equally as relevant. I often feel with these webinars, because my background's been in domestic buildings, and I think it happens a lot actually, commercial buildings tend to get neglected a little bit, but the issues are just as important, just as relevant. Often you're talking about bigger numbers, so higher flow rates, bigger ducts. Often you're also talking about, with something like a ventilation system in a commercial building, you're sort of concentrating, it's a big building and you concentrate a lot of the cost. So it's sort of added cost of, I don't know, 20 domestic buildings. So you tend to get people thinking a bit more detail about the design of the system. But I think actually measuring the performance of the system is still just as lacking in commercial buildings as it is in domestic buildings.
Absolutely. And also from Jeffrey, how big an impact could these measurements have on EPC ratings?
Yeah, I would say a range of 1 to 3 points in your EPC rating from measuring the air tightness. It really depends how airtight the building is and how airtight the RDSAP calculation assumed it would be. So there isn't a simple answer, and sometimes it'll actually get worse if you've got a really leaky building. But typically 1 to 3 points, and 3 is not uncommon, quite common. Interestingly, the RDSAP estimation method doesn't include anything about the age of the building. So it's difficult to give a straight answer to, and that's why I say it. I wrote a document about this as a piece on our website, a blog post about how much it would save. And one of the criticisms I got back is that I said 1 to 3 points rather than exactly this many points, but I'm afraid it's something I can't give a simple answer to.
Absolutely. The next question is from Marcus. You talked about the link between air tightness tests at 50 pascals and infiltration rates. Do you have any tested data to add to this, i.e. the dubious rule of thumb, such as divided by 20?
Yeah, really good question. I had a couple of slides about this in my first draft of these slides, but I felt it was, I had too many slides and I felt like it was ATT, but I think it's a really interesting topic. So there's not a lot of measurement out there. And when I talked about fundamental knowledge gaps, one of the big things I was talking about was this. And I think we're desperately in need of a reasonable scale measurement campaign where we do tracer gas measurements and air tightness measurements and see what real delivered ventilation is in practice. There's a couple of papers out there. There's one that immediately comes to mind by a guy called Alan Vega Passos, who was at Nottingham University, and I've done myself in a couple of test houses when I was doing my PhD. I did a lot of repeated tracer gas measurements versus air tightness, and what they're really showing is that the range in relationship between 50 pascals and normal use is pretty big. So for some buildings it will be as little as 1/40, and for other buildings it could be more than 1/20. I think it's got a lot to do with the exposure of the building, but it's quite unknown, I think. And it's also interesting to think about what is the best metric we want there. Do we want the average factor, if you like, 1/20 or 1/whatever number, or do we want to design for a day when there's, say, a calm day, cool day in winter, where you might have relatively little infiltration because you don't have that wind blowing over the building? So you sort of, when you do heat pump sizing, you design for the peak load. When we do ventilation sizing, should we be designing for the peak load or the average? So there's not a lot of evidence, and I would I'm sort of on a long-term campaign to be part of a project that does it. So very interested.
Okay, we're going to move on because I know time's starting to tick by. Another question from Tarek. Is it enough to use a vacuum cleaner from the outside, or would the cover need to be removed to clean a fan or vent?
Yeah, don't know the answer, honest answer. When I do, I take the cover off and use a cloth. Never tried a vacuum cleaner, but could work. I suppose a really company answer would be to say you ought to measure the flow rate before and afterwards to find out.
Taking it to the extremes now. And next question is, would you recommend residents to minimise infiltration in order to improve control over the environment?
Definitely the best practice and highest quality ventilation you're going to get is really airtight, low infiltration and deliberate ventilation. So you're in control of delivering air from a source that you're comfortable with and you're in control of to the building. So that is best practice for sure.
And we've had an observation through from Jim that you haven't mentioned prevailing wind direction, which is a guidance point in Part F, or wind pressure as it affects infiltration.
Yeah, I haven't. I'm in two minds about it. Certainly, I guess it gets into what I was from Marcus's question. It's quite similar. So if you're thinking about the average or typical level of infiltration, then the prevailing wind direction is really important. I think actually of our office, it's much higher up on one side than the other because it's built into a hill and it faces the southwest. So it's got really high exposure and you can totally feel it in the amount of infiltration in the office. So it's important. But if you're talking about the sort of peak level of ventilation demands, then of course the wind changes direction and it changes speed. And so then I get in two minds about how important it is. So it's definitely important for how much air movement there is. To be honest, I'm not decided on how it should be accounted for in the regulations. Yeah.
And Ivana's just mentioned, how come you haven't sorted out your office? It's been sorted a lot.
Yeah. Well, the office is an interesting building. It was built as an ammunition depot several hundred years ago, and it's a good test case for how you can't control everything, I'd say. So I think it's a lot better than when we moved in, and it's a good argument for ongoing monitoring and continuous improvement.
Thank you for joining us for this final webinar of 2025. If you have any further questions or would like to take background ventilation further within your day-to-day services, please do get in touch via the details on the screen. We look forward to exploring more topics with you in 2026.